started. Okay, welcome everybody to Blacklake, our second public demonstration. We did one back in January 28th. And I'll go over some of the differences and what we're going to see and cover today. Last demonstration, we showed the ignition of some solid fuels and talked about what the energy balance was, what the power density was. And those numbers are quite extraordinary. They're actually unprecedented power densities, unless you consider an atomic weapon. The power that we've learned is a number of features about the power that I'll cover. Fundamentally, in our last demonstration, we were demonstrating that we had a new source of power, that the kinetics of making the electron of the hydrogen atom go to a lower electronic state had been increased so substantially that we'd increased the power by a factor of 1 billion from our prior electrochemical embodiments of making hydrinos as a new power source. We were harnessing that energy as electricity, as a high electrical energy gain, and then we were working on getting the power density, that is the amount of power, like watts per unit volume, to a higher level to make it commercially viable. So there's more theoretical work that I did, and what this entails is creating a more stable form of hydrogen. As I mentioned, it means the electron goes closer to the proton. So they're oppositely charged. You have a positive proton and a negative electron. So if you want to look at it in terms of, say, physical analogy, say the Empire State Building, you'd have the electron at the top, you'd have the proton at the street level, and it would be the size of, say, a dime on a relative scale. And the premise is that the electron can move closer down floors, say to the 25th floor, if there are 100 floors for a representative example, and that would release about 200 times the energy of burning. So the theoretical sort of barrier to conception of that is a postulated equation developed back in the early 1900s that throws out physics and proposes the universe is entirely math. In other words, the universe is comprised of math, and abandons all physical concepts of what an electron really is, treats it as a singularity, meaning no volume, and having it everywhere at once, violating causality and a number of physical principles. So this theory that is applied and predicts these new states is the reinstatement of classical physical laws that are confirmed by countless experiments that our entire modern society is based on, and in particular, specifically, it entails the laws of Newton and Maxwellian electrodynamics, and it predicts, in fact, that you can have the electron go closer to the proton in defiance of quantum mechanics, which is mathematically postulated, and you can't explain the stability of matter except by definitions in the math, which you can't confirm directly experimentally, or even prove what the wave function is in that mathematics. It's purely conceptual mathematical. Conversely, or in contrast, this is an exact solution of what the electron is. It behaves as a current. Currents are well known to emit electromagnetic waves. For example, they can emit radio waves as well as a current. So in the same type of structure and treatment, the electron is treated as a current that's the source of electromagnetic waves for absorption and emission. And you match the equations of light, which are extremely well characterized and predicted under Maxwell electrodynamics. You match those equations of light to the source of that light, being the electron, and you can solve everything that's ever been measured on the atom, what they call the Lambda fine structure, hyperfine structure, magnetic aspects, being the Stern-Gerlach experiment with quantized direction of magnetic moment that flips parallel or anti-parallel to applied magnetic field in a quantized manner. All those things including lifetimes of excited states, exactly what an excited state is in terms of the electron current and the photon that's captured by the electron and re-emitted as light again. All that can be described exactly, which is not possible under the purely mathematical construct. So it does allow that particular treatment, classical physics applied to the atom, does permit the electron to move closer to the proton. So if the argument is it's impossible according to quantum mechanics, then the response is we're not using quantum mechanics, we're using classical physical laws. And it does predict this new phenomenon that is verified, and you will witness today that it is real and it is absolutely predictable and can be engineered into a phenomenal power source. So, the difference and the reason why this doesn't occur spontaneously under your typical observational conditions is that it requires a new mechanism, because the electron is stable to light, but it's not stable to transferring energy to an energy acceptor that can accept an exact amount of energy that the electron has to give up in order to transition to this new state. So we can go from, say, the 100th floor to the 25th floor if we put an energy acceptor of the right nature in proximity with a hydrogen atom. That is an atomic hydrogen versus molecular hydrogen, which is the kind you buy in a tank from, say, Linde or Prax Air or something like that. So one of the impediments of making it into a commercial power source over the more than a decade that we worked on it is that the rate that the electron goes down to new levels is very, very slow. Even when you put a catalyst in proximity with the hydrogen atom. The fundamental breakthrough that we started to demonstrate the initial aspects of that in the last meeting was that there's a way of making the kinetics become massive. And it's so massive that the fuel explodes. And we're going to show you that today. So we're putting on a very, very low voltage field. It's lower than the battery in a car. You can grab the electrodes. You can get a shock. It's very, very low. But the current is very, very high. So for about 50 millionths of a second, it's running about 1,000 times the current in a household circuit, maximum capacity 4 trips per. And that current creates a state of matter that I'll go into, and that basically creates a chain reaction for this or positive feedback, is more appropriate, state where the electron is favored to go down to this lower level, closer to the proton, at extremely high kinetics. So, we showed detonations, and we showed heat, and we showed soft X-ray emission that proved that hydrogen had these new lower states in the last demonstration. What's occurred since then is we've done some more measurements, and we determined some very important features. First of all, there is a very, very energetic ionization occurring. That is, all the gas in proximity of that solid fuel gets essentially completely ionized, which is an amazing event that at atmospheric pressure, high pressure, relative to what plasmas are traditionally created under those conditions are pretty extraordinary to get a completely ionized plasma with a very, very small amount of energy input. In fact, you wouldn't predict that unless there's some extraordinary release of energy. The plasma expands, and then we were proposing that the expanding, conducting gas, highly ionized gas, would carry pressure volume work into a set of cross magnetic fields with crossed electrodes, and that would separate the charges by virtue of their velocity going through the magnetic field. They would be bent in opposite directions, positive, negative, be separated. You get a voltage, you create current with that, and electrical power from the flow of the current to an external circuit. Well, since then, we did some more measurements. And it turns out, and this is actually a very fortuitous thing, that there is very, very little pressure When we let this off, if you're close enough to it, you can definitely feel shock wave. You feel pressure hit your chest. And if we get a very good one, you can even feel it through the wall in the other leg. But what's really unique about it is that it's extraordinarily bright. And we've been working on more advanced fuels. And it turns out that there's very, very little amount of the power to energy in the form of pressure volume. You say, what's pressure volume? Well, the internal combustion engine works by igniting gasoline. And gasoline is a hydrocarbon, and it burns the CO2 and water. And that causes the creation of a lot of gases from a liquid and a lot more molecules than you started out with. And those molecules create pressure because they're hot and there's a lot more molecules after the ignition. So those molecules push on the piston and they take the energy they release in terms of pressure and they push that piston down the cylinder and turn a crankshaft and then your drive shaft and then your wheels to a differential. So that's doing work by taking pressure and pushing it through a volume. That's called pressure volume work. So magnetohydrodynamic, which we're looking at as a mechanism to convert the power, does similar type of mechanism. It takes pressure and volume, but in the form of a flowing or rapidly expanding flowing ions, which ions flowing means current, and a magnetic field is equivalent of a motionless generator, where the motion is actually the ions. You don't have a spinning magnet in a coil, electrical coil like we do in an electric power generator in a central defense station. You have the flow of current being the ionized gas that's expanding. Well, there's very, very little pressure in that, which is good. So it initially expands at supersonic speed, which makes a shock wave. But if you measure the energy in that shock wave based on the pressure and the volume it expands into, there's very little work being done there. So then the question is, where is the work? Because there's an enormous amount of heat we can measure in the calorimetry, and we measure extraordinary amounts of light power, soft X-ray power, and energy balance when you convert it into electricity using photovoltaic cells. And that's the answer. It's really light. All those measurements, the optical power, the photovoltaic converted electricity, and the light, and the spectrum, and the spectral power measurement show that essentially all the energy released from that creation of these new states of matter, these new hydrogen atoms in lower electronic energy states, is being released as brilliant light. That's a very fortuitous thing. None of it's fortuitous for being light, because then we don't have to use the steam turbine, and we don't have to reinvent magnetohydrodynamic for our application. We can use photovoltaic cells. So that's the new thing. Photovoltaic cell electrical power conversion. We have that work. That's what we're going to show you today. So what does that mean for commercialization? Well, photovoltaic cells were invented in Bell Labs in 1954. So there's like 5 decades or 6 decades of work that's going into photovoltaic cells, probably $1 trillion, and we can take full advantage of that because that particular device has the capability right now, commercially available, that you can make somewhere between 500,000 and 1 million watts of electricity per square meter for something as thin as cardboard. That is incredible. In other words, the photovoltaic cells that you see out in the field, that take up the whole field, that's why they call it a solar farm, those cells are only working, well, there's other disciplines, but they're working about where they should be working, but they're a variant of that that use different materials that work at extraordinarily high intensity, at least 1,000 times higher intensity. So you want to think of it like a fiber optic cable versus twisted pair. Fiber optic cable has a higher bandwidth. It can carry a lot more signal. And these particular cells can carry the equivalent of a lot more signal, like 1,000 to 2,000 times what your run-of-the-mill solar panel cell would do. So we're going to use regular solar panel cells that detonate at very low frequency and store some of the power on the capacitor, so we get pretty much continuous production of electricity. But we are working with 6 photovoltaic cell companies to use these advanced photovoltaic cells, and we're using it in application, in particular commercial applications, emerging very, very quickly, and it's called the concentrating photovoltaic industry. And it involves concentrated photovoltaic cells. They have something called triple junction. What's that mean? Well, triple junction means that each layer comprises the junction. So there's 3 layers of materials in that photovoltaic cell. Each one of those layers is responsive to a certain set of frequencies or band of frequencies, or like wavelengths of light. So some of them would do, like, if you think of a prism, you know, you get red on one end and blue on the other. It would take red light to one layer. The middle colors for, like, green maybe, for another layer, and then blue for another layer. So it is responsive to different layers, therefore it covers more of the solar spectrum and it can be much more efficient. We are working in the field at over 40% efficiency compared to standard solar cells that are maybe as high as 22%, but the one we're using is 17%. So they're much higher efficiency and they operate at extraordinary high light. So that's basically what I have to tell you today. That we're making hydrinos, which is a new state of hydrogen. We have a lot of analytical data, I mean enormous amount, overwhelming confirmation, validation, and evidence that we're making a new state of hydrogen. That state of hydrogen, you say, well, where does it exist? Nature, it turns out our data matches exactly or fits to every measurement so far that it is the dark matter universe. The dark matter universe term meaning exactly what it means, that there's matter and it's dark. It's simple as that. You look out in space and you can see an enormous amount of gravity, but you can't see anything there absorbing or emitting light. Everything else is absorbing and emitting light, like hydrogen. So essentially everything you see, for all intents and purposes, is hydrogen. And then there's everything else that's showing gravitational effects that you can't see. It turns out that's about 100 times more than the amount of hydrogen you see. That's a lot. So it looks as if what we're making in the lab is incredibly ubiquitous throughout the universe. It's extraordinarily stable. It's just hydrogen in a new chemical state. And you can see it by techniques like X-ray photoelectron spectroscopy, where you completely ionize it with something called Compton or collisional ionization. And you can see it by its rotation, vibration. And you can see it by NMR, which is another technique. You use that for medical imaging, but basically it's looking at the energy level of the nucleus acting as a magnet in the influence of the electrons screening out an external magnetic field. So if you have electrons really close, as you do in this new hydrino or dark matter state of hydrogen, it causes a different NMR frequency than ordinary hydrogen, and that frequency is predictable. And all the data that I'll show and we've measured so far confirms we're making a new state of hydrogen in the energy level that's predicted theoretically from classical to physical laws. So that's it, new state of hydrogen. Here's the dark matter of the universe. It's perfectly safe, there's no pollution, there's no CO2. We're getting extraordinary powers, and you can convert that essentially all light. There's very little pressure volume, and you can convert that into electricity using commercial photovoltaic cells of the concentrator variety that run at thousands of times that of conventional solar cells. Now, how much energy and how much power are we making? Well, we're using, first of all, what are we using for fuel? We're using water-based solid fuel. What water-based solid fuel means is we have water bound in a conductive matrix. So what's conductive? Metals are conductive. So we have a metal powder, and then we have some inorganic compound like a alkaline earth halide. So what's that mean? Well, alkaline earth halide is things like magnesium, calcium, and halides like chlorine, like sodium chloride, table salt. That the negative ion is chloride ion. So if you can imagine magnesium chloride, like Epsom salts type stuff, magnesium, and chlorine from table salt, that's the kind of material we're using. It absorbs water very, very tenaciously. It's called hygroscopic, meaning it absorbs water. And it forms something called a hexahydrate, 6 water molecules for magnesium chloride. So we put that in, metal powder, and we run the 1,000 times household current through it, and you'll see what happens. It's pretty impressive. So we've now taken that fuel. This is another big departure, advancement from the last demonstration. And now we're running that as straight powders. We're actually using the fuel without a encasement. So in the prior demonstration, we had an aluminum encasement. And Johnny can go and introduce in a second. We'll run some in encasement just because it's convenient to do so. But the demonstrations you're going to see are not using encased metal powder with the inorganic compound that has found water. It's going to use the powder itself. That's very important, because the other thing we found is you can take this metal powder, you can run it through in a continuous manner, well, at least as fast as you can ignite the material, the solid, water-based solid fuel. With the systems we have, you can essentially ignite that as fast as the electronics for this particular power source, which is a commercial spot welder. And it turns out you can't really buy a commercial power source, a laboratory variant, because no one ever had any reason to use such power that form, low voltage and enormously high current. It just happens to be predicted theoretically to make this hydrino reaction work at extraordinarily high kinetics, and what we're doing is that's available from industry. So we've adopted that piece of hardware, and you can see there are 3 of them here, to power ignition of our solid fuel. So we're running powders through, and we're igniting that in a semi-continuous manner. So that's new. We're doing that by developing the mechanical and electronic control systems, the flow of power through, the run the current through the material in a sequential manner, so you get sequential ignitions and bright flashes of light. Then we're taking that, in another demonstration we'll see, and converting that into electricity. The important thing is that we can run these powders, we don't have to put them in encapsulated metal encasement. And the other major feature that we confirmed multiple times, over and over again, is you can take the powder fuel, rehydrate it, and reuse it. That's very important. So we have now shown that we can get extraordinary bright light. It's essentially the same light as the sun. We can convert that light, because it has that same characteristic as sunlight in terms of its wavelength composition. We can convert it to electricity using photovoltaic cells, running powder with ignition, and then we can rehydrate the powder and run it over and over again. That's pretty good. And we've also done other analytical characterization and identification of this new states of hydrogen. So that's what we're going to show. We're going to show the powder undergoing sequential, mechanically fed into the system and sequential ignition. Then we're going to show light production from the light flashes. So it's kind of a little bit circular, but you could have the electricity put into a car, or turning the propeller, or drive shaft on a train. Many applications. But right now we're taking the light, converting electricity, and showing it convert back to light again. That is lighting a light emitting diode. As I'll go over. The energy balance for that matches the energy that we're going to see in this calorimeter. So, how much? So I keep coming back to this question because I want you to think about it. How much energy and how much power are we getting? Well, what we typically have, and Johnny will pass around a little canister, is we put in about 20 microliters, 20 millionths of a liter. Most of that, almost all of that, is metal powder. And then there's a little bit of water in it, bound in the material. So basically, it's a small fraction of the bound water is transitioning to this hydrino state. So that gives an energy of about somewhere between 500 and 1,000 joules. And it's a little bit variable because it depends on how the amount of energy you get off depends on the kinetics and the yield of the hydrino transition reaction. That is, as I was saying, we have the electron at the top of the Empire State Building, 100 floors, say, for representative purposes, bring it down to 25th floor. So that will happen by transferring energy to an energy acceptor. I'll go a little more into mechanism in the PowerPoint. So it depends on how we flow the current through, and you'll understand that once I show you the mechanism, and how well it's confined and how long that current is passing through the material before it explodes and is no longer in contact with the source of electricity. That determines our yield. So he has to tweak that very carefully to a certain pressure and a certain volumetric displacement for that amount of fuel to optimize the amount of energy you get out. So there's some variables, between 500 and up around 1,000 joules. And it's about 20 millionths of a liter. And we measured with something called a fast photodiode. That's something that's looking at the light as a function of time with fast electronic detection. And it shows that energy is being released in about half a thousandth of a second, half a millisecond. So, if you take an average of, say, 700 joules, and you divide that by half a millisecond, which is 5 times 10 minus 4 seconds, you end up with 1.4 billion watts. So you get a peak power of 1.4 billion watts. You're getting 1.4 million watts of light for half a millisecond. So if you ignite at 2,000 times per second, then you will get 1 million watts of light. And that photovoltaic panel can convert that to electricity at about 400,000 watts of electricity. So if you have twice that amount of fuel, then you get 2.8 million watts, etc. 10 times you get 14 million watts of electricity. So that's a lot of power. But it's a lot of power in the context that the volume is only about 20 millionths of a liter. So when you take into account the volume, you're looking at about 140 billion watts per liter. That's unbelievable. I mean, that's incredible. That's the same power density as an atomic weapon. I mean, it's very small scale and very short time frame. So it's all controlled. We can detonate the fuel, and the fuel doesn't auto-detonate. Unless you run the current through it, or only where you run the current, that's the only fuel that'll ignite. If you're in a strip of the fuel, it only ignites in a section where the current went through. It's phenomenally safe. You say, wait a minute, this looks pretty big. This is pretty energetic. This looks like higher energetics than a high explosive. But it's only where the current flows through. It's only when the current flows through. And it's perfectly safe because it's just metal powder with water in it, basically. Salt, metal powder, and water. So have you ever seen rust explode with mixed with metal? Yeah, perfectly safe. It's just these particular conditions are what you need to transition hydrogen to this new electronic state and release that phenomenal amount of power. So, I'll go into a little bit more detail. So where this is going is, right now we're doing the continuous ignition with powders that can be rehydrated and recirculated, and we're doing that manually. We're converting the light into electricity with standard photovoltaic cells. We're going to show you that. The next step is we've already come up with an ignition system and regeneration system that's very simple, and we've already tested it and it works. So then we're going to implement an automated injection, regeneration, mechanical electronic system, so we can run this thing continuously, making extremely high power light. And we'll convert that into electricity with a standard photovoltaic cell. Then the last step is we take the photovoltaic converter, and those converters can run at high voltage. You put the cells in series, and you can get hundreds of volts. And it's DC voltage, and you can power condition that to run these particular devices. That'll be it. because then we'll connect the photovoltaic cell converter to our electrodes, through which the current flows and ignites the power that we're feeding in continuously, and we'll be regenerating, rehydrating, and feeding the power of this new ignition system. So that'd be it. It'd be self-running, autonomous, enormous electrical power, unsurpassed power density. So you say, okay, what's like 100 billion watts per liter? What's that? What's it come from? Well, it's 1,000,000 times higher than the internal combustion engine. And you say, okay, well, what good's the internal combustion engine? The entire modern society is based on internal combustion engine. Like, you think this electrical grid's really important? That's only like a fraction of a percent of what the world generation capacity is. Really think about it, it's a fraction of a percent. Almost all the power generation on the planet is basically internal combustion engine, and then of course heat. So ultimately, this is not what our modern society is based on. It's convenient and of course it's essential, but the main driver of the economy and the human standard of living is the internal combustion engine. It's 1,000,000 times higher. And the standard of living is directly dependent, or there's a perfect correlation, if you want to think of that word, it's like a function, input, output, more energy, more wealth. It's like a direct input-output relationship. So to get enormous more power per individual, you're going to have enormous more wealth. I mean, that's the theory. That's been held up absolutely perfectly from man horsepower and water power, wind power, and then finally, whale oil, and then coal, and then oil, and then some coal, and etc. So an enormous amount of power capability of man should have an enormous impact on the economy. Okay, so we're going to show some devices. That's where we're going with this. We think this is going to create an extremely big event in terms of creation of wealth and implementation in commercial power systems. It can be used for everything from cars, trains, planes, aerospace, everything imaginable. I'll come back more to that. And it basically probably can be miniaturized as small as you can make a photovoltaic cell. So how small can you make a photovoltaic cell? Real small. So it could be really small, really big. Right now we're focusing on 250,000 watt to 10 billion watt modular scalable system. The light we're seeing here is tens of thousands of times higher than the sun. And it's still factors of 10 higher than even these extraordinary photovoltaic cells can handle. Albeit they are coming out with new generation cells that could handle this kind of light. So we're going to use a fiber optic lens optical distribution system, cut the light down, and have those fibers feed photovoltaic cells. So that's really good because all that technology for telecommunications and high-powered lasers is already developed. So we're taking advantage of some extraordinary, amazing material science and commercial technology. It's the cutting edge of kind of human ingenuity. So we get to use all the good stuff, the lenses, the fiber optics, and the photovoltaic cells. We can make an expandable system. If you add more photovoltaic cells and you increase the power output by just putting more of these chips in it. Like a computer, you want to put more memory in, put more chips, you want more power, you put more chips. And everything else stays the same. So modular scalable system. Projected cost of manufacturing is about $100 a kilowatt. It's pretty much all dependent on the photovoltaic converter. That's essentially all the cost. And even that will pay for itself in about a month. So it's not, doesn't have the issues of solar photovoltaic. You can have a 20-year payback there because it's you're only getting electricity when the sun's up and it's not cloudy, and they have at least 1,000 times less capability. And I guess I should mention, in terms of the existing industry, there is this concentrating photovoltaic industry where there's tens of millions of watts of installations on some, even in some of these installations that are out there in operation now, and there's more and more planned, big installations, maybe a 100 megawatt type scale. The way they work is you have a huge parabolic dish of mirrors. And the mirrors focus the light to a very, very small photovoltaic cell section. So that's what we call the focus of the parabolic dish. And that might be 3 inches by 3 inches. It's really small. And they focus all that light from something that might be 10, 15 feet across into that one little region. So it's got enormous concentration of light. So rather than using photovoltaic cells, solar cells for that whole area, they use mirrors instead and have a commensurate decrease in the amount, a corresponding decrease in the amount of photovoltaic material. So it's concentrated into one small, highly capable area of photovoltaic capacity. And then they take 1,000 times more light because they're receiving 1,000 times more light from this parabolic dish. So it's something that's already existing. So we would take existing technology, and that photovoltaic cell can't tell the difference between a photon from our light source or a photon from the sun. So we would just use our light incident on those photovoltaic cells. So that's, I just want to establish that that is the existing industry, and we're taking that part and saying we're going to use that part in our optical distribution and use our light incidence from those optics onto those PV cells and make electricity. Okay, so we'll get on with some action here. This is Johnny who's going to show you some control and then some lights and solid.
So first of all, I'll show you this commercial spot model puts the low voltage, high current pulse through it, through a sample. We have voltage taps for either the electrodes, and underneath there's a white cover here, there's a Rogowski cable that measures current. And actually on the screen there, you can kind of follow along with what we're doing a little bit. The red trace, for instance, at the top is an AC waveform voltage trace. The scale of that on the left is 0.6 volts. You can see it's being applied across the sample there. And current, for instance, on this particular sample out of runs, but at 30 milliamps. Oil sample, I'm just going to run this again, show you that it generates that kind of trace. Then I'll do the code. Alright, so on each one, this won't be noisy on this point, but on each one I'll count down 3, 1 on 0 I'll go, and on the loud samples that's when the noise passes. So 3, 2, 1, and look up on your screen. You can see it actually takes 4 seconds of data, so you're seeing it zoomed out. When I zoom in on the waveform, you can see it's similar voltage to first pulse that went through. So 30 milliseconds duration. So I'm going to go swap up on this peak amperage. Peak amperage was 30 kiloamps roughly. It's actually 26.8 is the peak amperage. And voltage was about 26 minus 0.6 volts across the sample.
And that's kiloamps is thousands, 100,000 amps. So this will just take me a second. What's allowed? So if anybody don't have your earplugs in yet, go ahead and put them in.
ventilation because it does aerosolize the metal a little bit. All right, we're good to go. Three, two, one. So you can see in the waveform, actually, it's passing current through here, and if I zoom in, it's passing some voltage, very small voltage, again, like 26 volts. And then when the explosion happened, it forced the electrodes apart, and that's where you see a voltage spike. So it's essentially open circuiting the transformer that causes that. That's a reactive power swing pattern.
Doesn't go through the sample, it's already gone.
Yeah, generated shock wave goes 2 PSIG at about 13 inches straight from the sample, which you can see down here, and with 160 decibels of noise, about 4 feet away.
Say one more. Can you guys handle that?
Yeah. Right. Okay, good to go.
Good to go.
Three, two, one. And again, pretty similar properties on that one. Pretty low input energy, so get that energy. You can see the input energy here, input indentation is about 70 joules.
All right, very good. So we're going to set up some calorimetry and some salt X-ray experimentation. One of the things that would be worthwhile as we go on our web page, and I'll show you in the PowerPoint, is we video that under high-speed photography, something called a nano camera using photograph high explosives. One thing you'll notice is different than this, than some high explosives. If you go on the Los Alamos site, you'll see different explosives like pentarythmical tetranitrate EGN and RDNX and other types of these high explosives. They make an enormous amount of black smoke and sort of red, orange color, mostly black smoke, kind of a plume. You can see black smoke here, and you see white or bluish white light. That's the same kind of light as emitted from the sun. So it means it's much, much hotter than conventional high explosive, and there's no smoke because it's not a high explosive. It's entirely different. It's making neutrinos by, and then thereby emitting the extraordinary amount of energy, 200 times the energy of burning. So it's a much higher energetic phenomenon than typical chemical reactions, and it gives somewhat of a shock wave, and most of it is light. So as you can appreciate from our high-speed video, it's very, very bright, white light. And that's what we would create continuously and convert that into electricity using the concentrated photovoltaic cells. I'm going to show some of that in later demonstrations. So next, Johnny's going to take some of that material, and we have something called a bomb calorimeter, appropriately named. It's a calorimeter designed to take a very, very high, very fast, high energy, fast release, high power, and what they call thermalize that energy. So all the light is converted into heat, and we're measuring the heat by the rise in temperature of a water bath. So if you take water, water is extraordinarily well characterized in terms of what they call heat capacity, the amount of heat it takes to make the water rise at a given temperature. So from that very highly accurate measurement in temperature rise, we can measure very precisely how much thermal energy was released. So he's going to do that, sets up what they call a 1341R calorimeter, a commercial instrument that we modified for our particular ignition system. 2 electrodes and then a bracket to hold them for turning pressure in on that fuel pellet, like you saw here, to a specific pressure to optimize the energy release. As I said, it's depending on how long the current flows through and the nature of that current before everything explodes out of that holder. So the current's disrupted. So he's going to run that now and show you the run that generates a significant amount of energy. So we're going to run that and show you that. Then on this setup, this is called a grazing incidence extreme ultraviolet spectrometer. And what this basically does is measure a very, very special region of the spectrum. It measures a region called soft X-ray. Not like X-ray, like a chest X-ray, not like ionizing gamma radiation, but what it does, it is ionizing in the sense that it causes the outer electrons of the gaseous environment, the ambient atmosphere, to become completely ionized. And that blocks the radiation. Soft X-rays can't even go through a millimeter of air. They ionize everything and absorb it totally. So what this is we're expanding. You see a vacuum chamber here, this thing with the different ports on it. So there's a detonation and it's under high vacuum. So the expansion of that plasma is going into essentially empty space, hitting it out so the light can come out and you can see the soft X-rays. We have publications on our webpage on the calorimetry and on the soft X-ray emission. And what's really amazing about it is an enormous amount, super high percentage of the energy is coming out as soft X-ray. No chemical reaction can emit soft X-rays. Way too high energy by a factor of around 100. And there's no high field here. It's very, very low voltage. And we're making black body radiation. So the energy the electrons have are only on the order of 1 electron volt, 1/100th that of the light that we're seeing. So there has to be new energy states of hydrogen that explain that extraordinary high energy light. And there's a lot of it. It's not trivial. It's an enormous amount of light. This has incredible applications for photolithography, soft X-ray, short wavelength, light source for making computer chips. That's another application. It's a very, very unique light source. But we run that at high pressure. It becomes fully ionized, black body spectrum like the sun, and then we can convert that power into electricity. So in a commercial power application, we run high pressure photolithography, we run vacuum expansion,
And here we're going back to the expansion to show the high energy light, which is confirmation that we're making a new state of hydrogen. So, you take a look? Sure. And then so stop the loop. And Johnny, we're going to take your turns here running the calorimetry and the spectroscopy.
Okay, so this is a 1341 caliber reader. We actually use two different PIs, which are virtual instruments to measure the variables that we measure up here. One is the same KPI that I showed you over there. It's kind of the current and the voltage. We tap the voltage, which will raise above the water level in there. That's the temperature that has to be measured in the water. And then we have some cable up here, which is the current that goes through the system. And we can calculate the input power. The other PI is RBI, and this monitors the temperature, so we can see the temperature change once the sample detonates, and we calculate the amount of energy that's up. Ideally, we want to have this temperature going down at a slight slope, so that when the spike happens, when it's over, it'll start going down again. We calculate very accurate endpoints. It's a little difficult to maintain that temperature region, manually adjusting the temperature occasionally. And I think we maintain about an hour, but it's working up very slightly. But it still will demonstrate the effect that you want to see. Essentially, I'm just going to want to see an impulse through it, and then you can see and observe what happens to the temperature. And we can do a quick calculation here with the front panel. Once the trace has risen and completed, and get an estimate of the output energy from that system. I'm just going to do the same thing. And since this is enclosed, steel flange, you don't really hear anything from this. It's not. We can count them anyway. 3, 2, 1. Nice initiation, it looks like. So we see some current coming in and right down, and then structural happen, there's a voltage spike, it puts the electron apart. And the energy inputs, that point of initiation was 140 joules. As you can see from the energy integrator here, carrying over 140 joules. And you look, you see the spike developing. What we'll do is we'll beat that develop, it'll take 5 to 10 minutes to develop, we'll get the gaps, we'll get the endpoints, we'll run a quick calculation on it, this front panel here so we can see out there.
Okay, good. Hey, you want to get public down? All right, I'll start with the PowerPoint presentation, and then Dr. Ying will up down the system. He has to do it down an extraordinarily hard map down. And it's taking a little while. We have to keep the pumps off so you can hear me. And I'll try and talk over him. And then once he does his run, then we can turn him off again. We can come back and visit Johnny's Tower 3 and Dr. Who's speaking with the violence across. So Johnny's showing is there's about 130 joules of energy taken to ignite that pellet. So that was one of the pellets that we passed around. That's the aluminum encapsulated material. The particular materials we're using are metals like copper, titanium. As I said, there's a material in there that binds the water as a hydrate. And that's it. That's all it is. And we're running it in vacuum. We have a paper on our webpage that goes over all the details of the calorimetry and the design of the calorimeter, the methods and systems. It's extremely accurate. We run many controls. They come out to the energy balance. And we get an extraordinary large amount of energy out of this reaction. The theoretical energy for any known chemistry for many of the materials we're running now, such as in our demonstrations, we run under argon atmosphere, is 0. So this material will last, at least in terms of known chemical reactions, forever. Unless you have an air leak or something like that. And there is some of the metals we use, there is a reaction with water. The water can react with the metal, form an oxide. but the reaction is so fast. The time the reaction is occurring is phenomenally short time frame. So we go and measure using a technique called X-ray total electron spectroscopy, or we use X-ray diffraction, and we do not see oxidation on that time scale. The order is known from high explosive work for certain metals. The reactions are so fast, you just don't get oxidation of those metals on that time scale. So a conventional device is really using metals that have no chemical reactivity, so they would last indefinitely. Things like silver plus magnesium chloride, which is a hydrate, the other indicator are favorite. What Johnny's showing is 130 joules of energy to cause ignition with the aluminum capsule. Aluminum capsule requires, in order for ignition to occur, requires that it become molten. So we have to melt the aluminum capsule. That takes about 130 joules. If you don't use the aluminum capsule and use some of these other fuels, you'll see that we get the ignition with as little as 5 joules. So if we get 5 joules and 500 to 700 joules out, we're getting more than 100 times more energy out than it takes to ignite it. So even with a very low efficiency photovoltaic, we're very confident we'll be able to hook the photovoltaic converter to the ignition source and have a self-running system to net electrical power out. So that's called a parasitic load in the industry. It can be very, very small, maybe 1% to run the ignition, and then we have some other small load to run the mechanics, like drive motors. We have a vacuum pump or gas recirculatory system. We'd be running that off the PV generated power. So one of the things you can see here is the power supply is pretty big because it has a big transformer. It's made to last 100 years, and it's pretty much indestructible. We can blast these things off and have a huge current go back through the transformer. It doesn't damage it. It turns out that ultimately we'll be running the ignition off the photovoltaic converter, the DC power, and then we have the power, any reflected power, go back into the source of electrical power and recharge it up, so we recover all that energy. So really it looks like it'll take pretty close to 5 or 10 joules to ignite that. That power supply has already been designed. I'll go into the engineering after the PowerPoint, but we have 3 engineering firms engaged, and we have essentially all the system engineering done. And we're going on to detailed engineering, and we're testing the different parts, and you're going to see some of those parts that our machinist here, Jim, has made in our shop, and we're testing it in our equipment. So that is going extremely, extremely fast. We don't need this really big thing. We need a tiny little, like, flash bulb capacitor, like on a flash on your camera. Start it, 50 millionths of a second of electricity, very small amount of energy, and then turning off the PV converter. So that whole thing will replace with a little tiny matchbox kind of device. And that's been designed. So let me get on with the PowerPoint and go into more details. Oh, yes? Sure. Okay, Johnny's going to go over the power balance right now.
Okay, so it's actually, you have to look temperature, if you look at the mouse on the screen right now, you have the temperature slowly up a little bit. At the end of this experiment, it means slowly up a little bit because the room temperature is rising right now, and as they're optimally, you'd like it to be going down, so you can get some endpoints. You have a clock, so you know our starting point. Temperature is slowing down. Show them all. Yeah,
All done work? It's working?
that's not good. Essentially, this would hurt more and start going down and look at the water temperature. So you take a little bit of testing and you're always at this point, take it slow between starting slow upwards, not to the point where we initiated, and then take an end point, probably right about here, it's still just a touch of gas, but really in the end, it only makes a couple of difference. And then you can see the pulse slope still slightly increasing the growth. So when we take these data points, find the associated time and temperature, and plug them in, along with the 144 people energy. We calculated out. You can see that kilowatt energy out. That's okay. Okay, so I'm almost done anyway. So when we plug these numbers in at each of the points, associated points calculated, you see that you get an energy out of 821 joules. So if we take that input energy that we put in, the 140 our net is 681 joules out. And that's even about 6 times 5.7 times the input energy. Okay, good. John. What's the temperature delta of? It's about 2103.
It's good with what? Orbit credit. Very big band, very, very high average temperature. So that's the principle of how this operates. That's a very good signal for this particular application. Okay, we'll go to the PowerPoint presentation. So basically, everything that's projected about energy is now obsolete. That's got to be readdressed. And when we started out with the company, we were originally looking at making steam-type power plants, big power plants that occupy like 10 acres, have turbines bigger than this room, and big boilers. Or the boiler in a coal power plant is like a basketball court, maybe four stories high, so it's like the inside of a basketball arena. Now we're looking at extraordinarily compact, a million times higher power density internal combustion engine. The actual cell itself that we generate, the order of 10 million watts would be cubic foot, and it would have a photovoltaic system that would be expandable in modular fashion, and that could run everything. So what you're seeing here in terms of coal, gas, oil, nuclear, solar, wind, it's all in play. Our sources disrupt everything you see on that screen. So those markets are really what we're going to be making this modular system to do. So you say you get 250 kW, then you can do cars. 250,000 watts, it's like 333 horsepower car. The 350 horsepower, 350 horsepower car, 0.75, 750 watts per horsepower. So that's a pretty powerful automobile, and then you can put that 250 kW, you can scale it up to 10 megawatt. 10 megawatt would do biggest coal train, biggest cargo ships, biggest freight trains. Of course, in between we do freight on like tractor trailers, big trucks. Then on an airplane, you're looking at systems that are on the order of 100 million watts of rust, but you have the whole wings full of fuel, and those jet engines are very, very heavy. That jet engine was replaced by what they call a turbo fan. And you want to see one, there's something called an E-plane that Airbus just showed. It's sort of like an A4 trainer jet. They just have a two-man sort of jet configuration, and they have the jet replaced by turbofan driven with electric motor. They're running that off lithium-ion batteries. It's only 60 kilowatts of power, but it flies really well. and the technology, which demonstrates the technology is there. Everyone knows the technology is there for electric automobiles. It's there for electric ships. Submarines are electric. Nuclear electric. Aircraft carriers are electric for making the new generation Navy ships and other ships. Gas turbine and then electric. So that's well established. Trains are electric. Buses can be electric. So the technology there just needs a really incredible, great power source like we have. And I'll show you the mileage and the logistics. It's just phenomenal. So in a jet airline configuration, we have redundancy. Maybe we use 10 of those 10 megawatt units, 20. You have one go out, you're only going to lose 5% of your power. So that's a good thing. You don't have that luxury with conventional jet engine. They catch on fire, that's it. You lost your engine. So, the point of it is 250 kW, it's a 10 megawatt scalable modular unit can address essentially every major power market. And the mobile assets, particularly cars, specifically cars, are portable generators, and they can feed into a local mini grid. So let me ask you, would we be paying our electric bill if we could just plug those cars into the building? My answer would be no, we wouldn't. We would save $150,000 and we would just run our own power source and forget the grid. So I think that's probably what's going to happen. We're agnostic to how it's going to roll out, but that is one scenario. Because anybody who owns a car, if you have 250,000 watts of electrical power, you can make about $350,000 a year selling electricity. That's a big incentive. You don't have to work anymore. You just spend some on your car to generate electricity. A 10 megawatt unit can make like $15 million a year, so you get the point. It's very, very valuable as a generation asset. You can't do it right now because the car will wear out and gasoline is too expensive. It's cheaper to buy electricity when you burn natural gas or coal when you have big turbines. And even when you have half of it lost on the line and pay twice as much because you got transmission, it's still cheaper than buying gasoline. But that's going to change. And I do rethink the portable asset being in a car with a dual application. So, let's rethink. Hey, you want to do your console? So he's going to ignite it, and then we're going to come back and look at the spectrum.
This is spectrometer for very low wavelength photon. For using spectrometer. Power wavelength reading below 50 nanometers. And this is a glass chamber. The chamber on the side, the band, and holds two electrodes. And the sample will be reduced. We'll grab the linear electrode and we'll press that screen. When the electricity goes away, we'll and the spectrometer has a tool in the future to block the visible light going to the spectrometer. We are very unique soft X-ray photons. So we must be measured under the vacuum because the UV don't go to the as a temperature. Without spectrum required. The shortest wavelength of the photon down to 17 nanometers. 17 nanometers and equivalent to 70 eV electron volt. So with this small welder, we provide 15 volt and create photons with 70 eV. So the thermal energy comes from the blast on the hydrogen reactor, the only source for the subject. So based on our experiment, it's like the hydrogen reactor always comes with the unique photon emission. Or some actually, it's not possible for any chemical reaction to like this.
Yeah, I'll come back to some of that other discussion in terms of astrophysical evidence of the hydrogen reaction occurring in nature being a ubiquitous dark matter in the universe. Chris, going to turn the pumps on. So we do have some licenses with 7 entities, multinational chemical companies, utilities, and an independent power producer of about 8.25 gigawatts. And that scenario was back when we were contemplating doing central power generation, but now we're doing completely distributed power, albeit we could also feed into the grid using DC power, and then what they call inverters that would convert DC into AC, make it compatible with the grid. The same thing exists on windmills and on solar farms. So again, that's another technology that's been commercialized. It's been experienced economies of scale, and it's readily available if you wanted to feed into the grid. What's unique about our source is it's extraordinarily inexpensive. You can see here that the chemical cost could be a fraction of a cent. Be very, very low chemical cost. So just a summary, again, this is an application of using physical laws to solving atomic problems. And since the world as we experience obeys physical laws, obeys causality, it's made up of particles, electrons, and protons, they comprise neutrons that make up nuclei, and electrons that are bound to those positive nuclei. But all really bind together to form molecules and composition of matter. All that material obeys physical laws. So it's only natural to imagine that the constituents that make up that material also obeys physical laws as well. And it turns out that's true. And what it says in all quantum mechanical textbooks is physical laws cannot be applied and do not work at the atomic scale. And that's not true. It's absolutely not true that you really can solve atomic problems using physical laws. They didn't solve it correctly. They did not apply those laws the right way in solving the atom. It is not an easy problem to solve. So rather than say, well, we haven't solved them yet, they elected the current paradigm as a forfeiture in that it said, well, we'll just forget about it and we'll just make math. And it was originally proposed as a tool that we just use curve fitting, adjustable parameters to try and get some patterns in nature to try to project further patterns. People do that all the time with statistical models. That's what quantum is. It's a statistical mathematical model. It is not the electron. It's not an atom. It's a probability density function that has negative and positive values of probability. You have to square it to get any sense out of it. And it doesn't mean anything physically. It was never meant to mean anything physically. When people started interpreting, they get really crazy answers like there's spooky action at distance and lack of causality. Things can be in multiple places at once, on and on. And it's just because they're trying to apply something for which it was never meant to be applied. Once you solve these physical laws, all what they call spooky action, entanglement, multi-dimensions, renormalization for affinities and all these kind of wild magnetic concepts go away. It's perfectly intuitive, simple math, absolutely predictive. And it's deterministic. It's not, you gotta ask yourself, why does the atom always have exactly the same energy if it's based on a probability? Well, it's because it's deterministic, it's exact. This is some of the computer rendering of what the current of the electron is, right? So this is an approach where the electron is solved as the source current of emitting and absorbing electromagnetic waves. And it predicts all the phenomena of atoms, of multi-electron atoms, of chemical bonding, and on and on. It can solve molecules identically. It cannot solve any molecule using current theory. It's all semi-empirical, computer, computational, adjustable parameter theory. And the distribution of charge in space is not even distribution of charge. They say the probability, and we'll interpret that as a distribution of charge. It doesn't even match with images of molecules and the like look like. This solves every single electron, all the atomic electrons, all the molecular electrons, gets all the charge distribution, the magnetic properties, kinetic energy. Every single aspect is solved simultaneously. That is not true of current theory. Current theory would predict you cannot image molecules. You can, so I'll show you. So you say, well, how good is the current theory? We can see maybe 1 or 2 points on that line, and then it would be rolled out as poster child's how great the theory is, but you can see it's purely random on the right-hand side, how the computation results of current atomic or molecular theory. And on the left, you can see the classical predictions match to a part per 100,000, the limits you can measure, and it's analytical. It's the exact solution. It's not. There's no adjustable parameters in this approach. That's trillions and trillions of difficulty than just saying I'm just going to make some computer just match data by arbitrary computation. So this, by overwhelming odds, is correct because it gives the correct answer for everything it's tested against, and there's nothing you can adjust. It's an exact solution. So as I was saying, the current theory says you can't image molecules, and molecules look really fuzzy, like you couldn't image them, and now the technology is advanced, and you see on the top there you can actually image pentacene, for example, and there's many examples. You can look at IBM. They have even a movie where they move the atoms around, and they're playing tennis with an atom. One of them says you can never image an atom. An atom's everywhere in space simultaneously. It can't really exist. You got to collapse wave functions, all esoteric math. And there we are. You have an image of it, and on the bottom screen, superimposed is the electrons superimposed on that image. So the electron is not a singularity. Singularity means it occupies no volume. So the current theory is the electron doesn't even occupy volume, but it's everywhere at once. It's some kind of wave function, whatever that means. You can't buy that at Walmart or off eBay. But you can buy electrons. These are electrons. You can buy that. You can buy current. You can buy magnetic field. You can buy electric field, that is voltage. You can buy that at power companies. So what I'm talking about, physical worlds where you can actually buy stuff. It's really tangible. And the electron is a membrane. It's not a point. It's a two-dimensional membrane. So in an atom, it's like a soap bubble, and it's ionized. It's like a planar disk, and it has a certain current. It's really difficult to calculate, but you can solve that analytically, and when you predict the properties, everything has been measured on atoms, free electrons, molecules, and all parameters from subatomic particle masses predicting the acceleration of cosmology match. It's 1 followed by 85 zeros on scale. This works over. Even if you want to say, well, quantum, let's use that. It only works at the atomic level. It doesn't do anything macro, that's all classical laws. Doesn't do anything cosmologically. Doesn't predict particle masses. Doesn't predict origin, gravity, weak force, strong force. They're all hodgepodge, ad hoc theories. Cosmology, for example, right now is 20 adjustable parameters. And it doesn't even make sense internally. It's not even internally consistent. So this works with everything, subatomic particle gases and cosmology. As it should. I mean, there should be one set of physical laws, and it should work for everything, and it does. So this is showing a schematic of how the reaction works. So the blue entity here is how does it work? Here it is. So the blue atom is the hydrogen. The blue entity is the hydrogen atom. It's going to transfer energy over this yellow entity, which is an energy acceptor. We call that a catalyst. So ordinarily the hydrogen atom can't emit energy by emitting light, but it can transfer energy to an acceptor by a what you call a dipole. What it means is basically, let's say you take a magnet and push another magnet, or you take a collision, if you take cars, you can transfer energy. They don't involve photons. You generate power. You have a magnet spinning in the presence of an electrical coil. The changing magnetic field gives rise to electric current in that coil. That's billion-watt power generation in a central generation power plant. That's how it works. So you're transferring energy through space, not involving light. You don't see a billion watts of light inside of a generator. So the same principle occurs on the atomic level. You can transfer energy through space, not involving light. So something's got to accept it. Well, the amount of energy you have to transfer to make this hydrogen state is really, really high. It's higher than the energy that would ionize any known atom. So the electrons are ionized. You can see that's the other entities here. These electrons are being ionized in these atoms. So what happens is when these electrons ionize, you build up what you call space charge. Space charge means like if you're sliding across the rug and you touch a filing cabinet, you feel a shock. It's because you build up some extra electrons on your body. And you discharge it when you touch the grounded conductor, like a filing cabinet. It hurts. But that can build up to infinity and it will kill you. Luckily, it's limiting. So in this case, it's limiting as well. So you build up the space charge. The problem is it stops the forward flow of building up charge. But that stops our reaction of making hydrogens. So with this particular state, where you heard that big explosion, what's going on there is we're passing a very, very high current. And when that material melts, you get extraordinary high current in the conducting material, namely the metal. And that creates something called a arc plasma state. Arc plasma state has something called a negative resistance. Negative resistance is kind of a bad term, but what it means is if you look at something called Ohm's law, if you try and put more and more current, like a toaster, like you try to put more current, it gets red hot, and it actually impedes more current going through. It takes more and more voltage to force more current through. That's called Ohm's law. So typically, higher current, higher voltage. Voltage is joules per coulomb, energy per charge. The negative resistance state is the opposite. The more current, the lower the voltage. That's lower energy per charge. The more current. That's a positive feedback. Because this is creating electrons. It's ionizing stuff. You go. So you can imagine if you say, okay, if I can make more current, this thing's going to go faster. So the kinetics become very, very high. They go massively high, and the fuel explodes. So you want a good analogy. This has nothing to do with nuclear. No nuclear involved here. But if you want to give an analogy, you have 2 neutrons, and a 4, and an 8, and 16. Chain reaction. So it likes neutrons. More neutrons, the faster it goes. Here, it's electronic. The more electrons, the faster it goes. So it explodes. Same as way as you have a chain reaction, it explodes as well. That's why nuclear power plants are potentially dangerous because they can run out of control, like Chernobyl did when you try to turn the power up. So there's just a narrow region where you can run them in terms of the rate, or they'll cause catastrophic problems. This, the higher you go, the more power, the more light. It's limited to the amount of fuel we have. You don't need an atomic pile to get enough neutron flux to get the reaction self-sustained. This works at pretty much any scale, as long as you create those conditions. So light, electronic transitions of atoms are very, very fast. The electron goes down and light goes off, poof, to infinity. So it's gone. Here, near proximity, you build up charge, you put this arc current state on, it eliminates that charge, so electrons drop down real fast, just like they do with electronic transitions where they emit photons. That is the key to getting this enormously high power release. And it comes out as light. As Dr. Liu was saying, it makes soft X-ray. Soft X-ray ionizes the gas, and then the gas emits white light that we convert into electricity. So this is showing a spectrum down here. I wish I had a pointer that would work, but okay. So you can see there's a broad band of light here, all frequencies, and on top of it are spectral lines. The reason why there's spectral lines is because the soft X-ray is ionizing the atoms that are there. So you see a broad band of continuous wavelengths and then ionized stuff. The same thing is observed in the sun. The sun has a gas around it. You see spectral lines. People say, oh, it looks like it's 2 million degrees. Why does it look like it's 2 million degrees? Because there's stuff that's ionized that takes 2 million degrees of heat, a thermal temperature, in order to lose its electron. Or it could be really cold, and the soft X-ray could be absorbed, and then it gets ionized. That's really what we think is happening. That's why the sun, if you take other independent measurements, like look at molecules and stuff in the sun, it's really cold. That's the uniqueness of the sun. Where's that heat coming from? If the surface is only 6,000, how can the gas around it be 2 million? It's not. It's not ionizing because of thermal, it's ionizing because of this high energy light that's ionizing. So we see that in our experiments. So it's another mystery of astrophysics that it solves. So what's going on is those stars and sun is creating hydrogens. Why? Because we see exactly the same spectrum from those stars as we see, you just saw right now. Continuum bands of light with specific energy cutoffs. So that dark ring there is actually dark matter. So what's dark? Well, that's it. That's the Hubble Space Telescope, European Space Agency did a study. And you can see there's a ring, and you'll see in that ring there's galaxies that look kind of stretched out. These little kind of blobs of light. They're stretched out because they're not there. They're being gravitationally lensed from other parts of the universe. How do you know that? You change the angle of the telescope. It doesn't move the way it should. It's because it's somewhere else. That shows there's an enormous amount of gravity there, but you can see there's nothing absorbing or emitting light like all the background blue stuff. That's hydrogen. So that's what dark matter is. It's stuff that's dark and it has enormous gravitational field. That's how you can see it. You can see it by the mechanics of galaxies. You can see it by the mechanics of galaxies that collided and reform massive gravitational bodies. And that proves it's hydrogen because those bodies have essentially all dark matter in it as well. So astrophysicists are saying the only way that's possible is the hydrogen, this other form of hydrogen. They claim it's another form of hydrogen. It has to be the dark matter, and it has to be intergalactic. The only way it can be hydrogen is that it has some unusual property in terms of the way it interacts with light. But it has to be hydrogen because there's so much of it, and it's intergalactic. The only thing it could be is hydrogen. So that and other collision data, the way it collides, the way it behaves, the galaxies interact with each other when they come into collisions, all point to it being hydrogen that has some unusual property that doesn't interact with light like normal hydrogen. And that's exactly what we're saying. We're making a dark form of hydrogen. So it's a ubiquitous material, extraordinarily stable, not like CO2, it won't absorb sunlight, doesn't interact with biological or any systems, it can't chemically bond, it's the most inert stuff in the universe. But you can see it by a number of analytical techniques. And I'll go over some of them. You can see the energy of the molecules, the forms of molecule of hydrogen with a very, very short internuclear distance. It's a reciprocal integer of the internuclear distance of ordinary molecular hydrogen. You can see it rotating and vibrating in different types of spectroscopy. You can ionize it and measure how much energy it takes to remove the electrons from that molecule. It tells you what the original energy was in that molecule. It's 16 times that of ordinary molecular hydrogen in both cases. So this is a video of the plasma taken at 6,500 frames. This is high-speed video with a phantom camera. It's a camera they use to film high explosives, for example. And it makes white, blue light. If you look up on the internet,
matter physics book. White blue light is around 6,000 Kelvin. That's the temperature of the sun. If you look at the sun when the sun's going down, they show kind of orange. That's because it's coming through the atmosphere. If you look at it high in the sky, white. Same as this. Very, very high temperature, very high energy light, and can be converted into electricity using photovoltaics. So you go to a power plant, you burn coal, you say, why can't they use photovoltaics in a coal plant? Because the light it's emitting is infrared. It's not high enough energy to use the photovoltaics. This is a unique reaction by virtue of showing, or again, by virtue of emitting this and showing observationally this enormously high energy light, much higher than typical chemical reactions. And Dr. Blue said, we expand that in the vacuum, we get soft X-ray, no chemical reaction in the man makes that kind of high energy light. You can't, based on the energy of those energy released in those types of processes. So we can harness that energy by using photovoltaics. So the photovoltaic converter cannot distinguish our photon. Photon is a packet of light of a certain energy and wavelength. It can't distinguish our photon from the photon of the sun. So it'll behave similarly. And we have much, much higher intensity. So we're using an optical distribution system, which I mentioned earlier. And there's an overlay of our spectrum and the spectrum of the sun. To make that a point that we can use our light in substitution or replacement of the sunlight to power the incident upon power photovoltaics, allow them to convert that light into electricity. So this is one example. We're going to see this today. This particular demonstration unit was detonating solid fuel pellets. They're each about 700 joules, as Johnny was showing. There's a range, 500 up to 1,000, but on average about 700. They were detonating about once every second. So two things. Let's say you want to do validation of what I'm saying is accurate or not. First thing you'd say, now I go to Lewis Elmo's website, I see a conventional high explosive makes a lot of smoke, like red, kind of orange light. This is different. Very, very bright, very white light, so it's very much higher energy. Then you can say, okay, they're making soft X-ray, so that has come from an unknown chemical reaction, a new electronic energy state. Then you say, okay, how much energy are they making? So I can look at that photovoltaic panel. That was 70 watts of light-emitting diode light. And you can see they were on pretty much the whole time, albeit every detonation was about 1 second, or 1 hertz. Each one of those optical pulses is about half a millisecond, or about 5 times 10 to the minus 4 seconds. So there's a very, very short pulse of light, and the energy was stored in the capacitance in the photovoltaic converter, and it was emitting light of about 70 watts for 1 second. 70 watts is 70 joules per second. Times 1 second is 70 joules. We're using a regular solar panel. That solar panel is 17% efficiency. We have the model number on our paper on the webpage. But we're putting a Lexan glass shield, like you can see here, in front of that expanding plasma to protect the solar cell. And we don't have a quarter wave plate or any kind of filter like a camera. You see blue on the lens. It looks blue because it has something called a quarter wave plate. It matches the visible light that allow it to go into the lens and not reflect. Otherwise, if we didn't have that, it would go blue and just be reflecting a lot of light. So we don't have that on our Lexan shield, so it's reflecting about 40% of the light. So 60% times 17%, you have about 10% conversion efficiency. So if you take 70 joules divided by 0.1, you've got about 700 joules. And that's what these fuel pellets are making. So just from looking at that photovoltaic converter demonstration, you can tell that each one of those little tiny pellets is making about 700 joules of energy. That's being emitted as light, being converted to about 10% conversion efficiency, including the solar cell efficiency plus the Lexan reflection, and you can get your energy balance from that. We've also measured the spectrometers by extreme ultraviolet,
energy balance, and a number of different redundant techniques, including the calorimetry that you saw today, and they all match. It's making that amount of energy. It's a new power source of nominal power density that's light and can be made in electricity using PV. So one thing to watch about this, it got stuff a little dark. But if you look at the beginning, or the top of the blast shield on this is making light for 5 times 10 minus 4 seconds, 0.5 millisecond, 0.5 thousandth of a second. So that's a much shorter time frame than you can actually see with the camera. The camera's about 33 frames per second, but you'll see the white light go over the blast shield. That's because it's actually blinding the camera. So one thing that's interesting here is that it's white light and it's. You go over the blast shield. Show that again. Look at the top of the blast shield. So that's pretty extraordinary, because what it means is all the light is coming out of the system. It's not trapped in the electrodes, so the light is actually being emitted, so it can be incident upon the PV detector. We did a calculation, if it didn't expand like that, we'd only get 80% of light. There's a lot of engineering issues that have come up with our engineering firms. We have 3 of them. As I said, we've always been through the system design engineering. We're starting the detailed CAD/CAM design for commercial product, including 250,000 10 megawatt electric scalable module. All the light comes out, the heat transfer issues, the fuel regeneration, many, many issues that came up in terms of this system. All of them, as the engineers are saying, we're just either incredibly, this is either meant to be, or it's just phenomenally lucky, whatever you want to call it. But every single engineering challenge is broken in our favor. Like the existing technology, the way this thing behaves, like every single seemed like to be a difficulty engineering has just blown with instant solution using known application to the way the system behaves. So we're phenomenally either lucky or extremely big reward for our years of work. We like to think about it. So this is what the design looks like. Now the commercial design is probably going to be somewhat different than this, but it does show the working components, and that's really important. It has on the outside, but basically it's got a photovoltaic inverter. The PV companies make photovoltaic inverters with their heat exchangers, and then this is the water reservoir. This is a fuel regeneration chamber, and we would bring the fuel in this pipe, put it in this regeneration chamber. There would be water dripping down here, all incident on this hot heat exchanger outlet. It's coming from the heat exchanger. It's hot, coolant, makes steam out of the water. Steam treats more or less. The fuel regenerates, and we put it back up here in this fuel reservoir. Drops down from this fuel reservoir, and then there's a power supply here that electrifies the electrodes, runs a high current through it, and then we get the ignition. This is showing these bars, little bars here, there's 2 of them, positive, negative, are going into this power conditioner, and then they would supply some of the power, like 1% of the power would go to the source of electrical power, and the rest would go out in these terminals to the load. So this is showing a cutaway. We were initially envisioning gears. The problem is with the gears, the teeth got blown off like one turn. But then we went to rollers, and the rollers seem like they're infinitely survivable, and you'll see some material build up. If anything, we probably have to dress that they call dressing, which is really a good problem. Engineers love that problem because basically the wheels are indestructible. They just keep going on forever, but we're putting metal powder in, and the metal puts a layer on there. They're not going to wear out. You're just going to take like this material that keeps coating itself and dressing it, and it preserves the wheel. So that's another thing that broke in our favor. So we're using rollers now. But the concept is the fuel comes in here, and then current flows. Let's work out a way to get a pointer next time. So So the fuel comes in here, and the current comes down this bus bar through one electrode, and then the other, It goes back to the power source of making circuit. And we get, like Johnny was showing, 25 to 30,000 amps. And then you get this huge ignition, light, and then that goes to the photovoltaic converter and back. And that's basically what we're going to show. Now, we have the fuel dropping down. We go, there's dust. You might as well a little bit of dust. It's not like black building smoke. There's a little bit of metal dust. And that would go down the chute into a collection region here, and then go back for recirculation in this reservoir and then back into the fuel chamber. So this is again showing some labels of what I just went over. And then one of the applications we can envision for the 250,000 watt, which is 333 horsepower, about 350 horsepower, thereabouts. That will power very nicely this SUV. So here we're showing the cell here, and then we have the traditional systems in electric vehicle, transmission, and then there's a power controller and electric motors that drive these wheels. You can have independent electric motors on every wheel, so it'd be very, very sporty, very high torque, high performance vehicle. So this is going to go through, show you that concept. Now the fuel drops down, it's ignited, and then the ignition product flows down the chute into a reclaiming chamber, and then it's transported to the regeneration chamber where it's treated in water and then recirculated back into the fuel reservoir, drops down to another cycle. We've done this many, many times. All we have to do is rehydrate the fuel. So as I said, we have a design to combine this ignition system and the regeneration system very elegantly. And we tested that, it works, and we're going to be implementing that in our next demonstration. So our next goal is that a self-regenerative system, then hook it to the photovoltaic converter, and then we have a fully autonomous pre-production, pre-commercial demonstration prototype product. And we have component manufacturers, assemblers, make those parts, assemble it, and then we're ready to go to field trials, and then ultimately selling electricity to distributors. So that particular vehicle has an advantage, unlike gasoline-powered vehicles, of 3,000 miles per liter of water, taking the Tesla S, which is supposed to be a pretty sporty vehicle, as a representative. You can see the wavelength there for what the amount of energy per mile in the Tesla S, and converting that into volume of water equivalent. So you have enormous horsepower, unlimited range. Using water as the fuel source, you can acquire the water from the ambient atmosphere. Those materials that we're regenerating literally suck the moisture out of the atmosphere. Very, very quickly. It's a very, very high kinetic, very chemically favorable reaction just to suck water out of the atmosphere to regenerate the fuel. The atmosphere is typically 3 to 5% water, which you're breathing right now, living. So there's extraordinary abundant water. We picked appropriately the 6 Mile Bridge. I don't know if anybody recognizes that. Going down the Keys, because you're basically driving over water. The planet should be called water, not Earth.
So this is a continuous detonation kind of mechanical ignition system. We're going to show you that. And then we're going to put a PV converter on that, right down the station. So that's about 1 RPM, 2,000 RPM, they are 2,000 times that speed. You can imagine that power needs a 2,000 times that. It's a lot of power.
I just have a question about the power.
Yeah.
If you're in a company car, if you work out the mechanics of rather grabbing the shooting stuff.
You'll be able to spin pirouettes in an F-15 or whatever it's replacing. Pirouettes, I guess. Pirouettes? Yeah. So, just very briefly, putting it in perspective, current power supplies, power sources are always limited by something. Electrochemicals, the cathode reaction, you can't get more because of the kinetics, about a kilowatt per liter. Combustion, you have to bring the coal in, burn it, bring the exhaust out, it has to take the sulfuric acid and other ash and whatnot, pump the smokestack, and it's all kinetically limited. So then you have to, it's huge scales, you have to watch for heat gradients, melting things, whatever. So you're limited about 1,000 watts per liter there. Gas turbine, you're burning, that's getting to be the predominant new power source. It's using frac gas. There you're limited, maybe up to 5,000 watts per liter because you're bringing gas in. Air has a very low heat capacity. That means it takes very, very little energy to hit gas molecules very, very hot, and then it can melt the turbine blades. So historically, the way power technology went is you had a grinding mill. You just had to get this one water over this wheel, and you start making steam, and then let's get the steam, make some pressure, and turn the wheel. And they said, okay, let's just burn the stuff right inside the wheel. That's what a gas turbine is. They're burning the stuff right inside the wheel. So it obviously it's a challenge because you're burning it literally with blades, and they're surviving inside this intense fire. So and then you got to get the air in, the heat. You can't overheat it or melt or get irrevocably damaged. Now fly apart, crash, burn, like we're inject. So it is kind of tenuous when you think about it. Flying, you're actually burning stuff inside the engine. And then you got to get everything off. So it's limited, and that's about what's happening. Nuclear, Chernobyl showed you can't get the grade up too high or go out of control and catch on fire, and make it so you can't live there for 100 years. So internal combustion engine is actually the greatest thing that's ever invented. Power technology is extraordinarily hard to compete. People working in fuel cells and stuff, always, I know they've had insurmountable challenges trying to compete with internal combustion engine. They're never going to be able to do it. It's just too cheap. It's too high power density. But we're 1 million times higher than that. So the reign of the internal combustion engine is over. Blackplate's going to replace it. That's what this slide's about. So, I talked about applications. It's as small as you can scale down a solar cell up to very vast, commercial airliners, everything in between. And we're making a 250 kW to 10 megawatt modular unit to serve those markets. Last but not least, this is just showing this dip here is at the rotational energy of this new form of molecular hydrogen. And there's other examples of that. So this is a signature that's predicted for a new form of hydrogen. We have this run at multiple labs, multiple instruments, including the instrument manufacturer. And everyone's looked at it. Noted experts in spectroscopy said there's nothing known to man. It is hydrogen. There's nothing else you can assign it to, even theoretically or existing. And then the other thing we have is rotation, vibrational energy levels. These are all the predicted levels. And you can see these lines and where the peaks are. It's a whole series of peaks. It's not just one random peak. It matches the whole entire spectrum and its intensity. So the chances of that are so astronomically small, and it only shows up after we run our reaction. It is the rotation vibration of hydrogen. It's 16 times that of ordinary molecular hydrogen. And we get exactly the same spectrum every time. Then you can ionize it.
And that peak here at around 500 electron volts is the energy of the electrons in this new form of hydrogen. Ordinarily, electrons of hydrogen are around 31 electron volts. That's just standard energy. But this is 16 times that, around 500 electron volts. And we can actually show that as a new peak in X-ray electron spectroscopy that is unknown demand, doesn't match anything known in the spectrum, and only occurs after we run our reaction on a recorder. That is, it's not even in the reaction. We expose the material that absorbs it to the gases from the reaction, and then we show this new form of signature shows up, and nothing known. No one's ever seen this in any other circumstance ever. And it proves that we have a new form of hydrogen from our reaction. Matches perfectly the theoretical predictions. So that being the case, we'll go back now and first Dr. Liu covered the X-ray. We get soft X-ray emission. It can't be explained by anything known, and it's characteristic of and identifies, proves we're making a new state of hydrogen. We had other scientists, engineers come in here and they say, oh, that's all I got to see. Hydrogen is emitting soft X-ray. So we know hydrogen emits the Thun, the Passion, the Bomber, the Lyman series of lines. These are discrete spectral lines. Now hydrogen's emitting soft X-ray. That means it has new energy levels. That means quantum mechanics is dead. Because the way theory works is you find one example that disproves the theory is irrevocably dead. So that's it. There are new energy states of hydrogen, so it can be instantly by the soft X-ray emission, and these levels are predicted by classical physical laws. So this is absolutely perfectly theoretically allowed and confirmed by all these different spectroscopic techniques. So to further confirm it and to show you the beginnings of the emergence of this as a technology, we'll go into the next room. We'll show you the sequential mechanical ignition. Then we'll show you light emission, and we'll come back to the one we saw with the sequential light emitting system, and then put a full voltaic converter and show you light in that system as well. Then we'll come back here after those three demonstrations, and we'll go over question and answer, and we have some guests here that will take your questions as well.